The combustion chamber design also affects on the combustion process significantly, the flame speed in particular. Accordingly, you could avoid knocking by having the right combustion chamber geometry, as well as locating the spark plug at the right place. And we call the upper half of the combustion chamber the cylinder head, and the lower part the piston crown. And when it comes to design of combustion chambers, so the major considerations to increase the flame speed, the minimum flame travel, the traveling distance should be optimized, and exhaust valves and spark plug, we keep them close to each other because the exhaust gases are at high temperature. Therefore, the gases near exhaust valve are at high temperature, so that the high temperature gases near spark plug, if the spark plug is located near the exhaust valve, these gases are also at high temperature. Therefore, that makes the ignition easy at the beginning. And we need to create sufficient turbulence, of course, and we have to have a shorter combustion duration, quick burning, and we'll have to have the same burning characteristics in all cycles. High volumetric efficiency at wide open throttle conditions are required to produce more power, and minimum heat losses. Usually the heat is dissipated from the surrounding wall area, so we try to minimize the area to volume ratio. So if you can have a geometry where you have a larger volume with a small surface area, that would be ideal as far as the heat transfer is concerned. And of course, if you can design an engine which could run with low octane fuel, that would be also ideal, so that you can increase the compression ratio even with the lower octane fuel and get more power. So those are some of the most common shapes that we find in internal combustion engines. The wedge shape, which is very common shape in most engines, and sometimes hemispherical shape, the crescent shape where the piston has a ball in piston to increase the squish, as well as in the case of diesels to consider it as a pre-chamber for combustion, initial phase of combustion, and the ball in piston. So likewise, there are several different types of combustion chamber geometries used in production engines. And this graph shows, this one shows the burning ratio, that means burning angle, that means combustion duration normalized to one particular type of combustion chamber shape. So this is the dish type, open type, hemispherical, ball in piston type, and this is the spark plug location. And this one gives you an idea about the effect of the shape as well as the location of the spark plug on the combustion process. So in some combustion chambers you can see the duration is shorter. For example, open center model, the spark plug is at the center, and there's a open combustion chamber. There is a shape on this type of shape on the head, as well as this kind of shape in the piston, and it has a shorter combustion duration in general. But compared to, for example, hemispherical one, this one with the 1/3 spark plug, as you can see, the ignition delay time is much less in this hemispherical combustion chamber compared to open center type combustion chamber, for example, even though open center gives you shorter combustion duration. That means it burns 10 to 90% quickly, but takes long time for the initial phase. Like that, the different phases of combustion process is affected by the geometry and the spark plug location. So, of course, these different combustion chamber shapes have their own advantages and disadvantages. So, the developers look at these different configurations when it comes to deciding what should be the best shape for a certain engine requirement. Okay, let's move on to the combustion in compression ignition engines, that is the diesel combustion, which is somewhat different to the combustion in gasoline engines, which is a pre-mixed combustion where air and fuel are mixed together well before the ignition takes place. But in the case of diesels, of course, we inject fuel at the end of compression stroke. Therefore, there is no homogeneous mixture preparation as in the case of petrol. So, the diesel combustion is not a pre-mixed combustion. The flame diffuses into the unburned gases rather than flame propagating starting from one point and propagating all across in the case of petrol. So, as we discussed earlier, the diesel, of course, we can operate at very high compression ratios because the combustion duration is much shorter in the case of diesel. Unlike in the case of premix combustion, we promote auto ignition. The diesel ignites on its own. There is no spark ignition in this case of diesel combustion. Therefore, we could go for very high compression ratios. So, as I mentioned, the fuel is injected into the compressed air at the end of compression stroke. So, the pressure and temperature is very high in the case of diesels at the time of injection, and so the injection duration is more or less about 20 degrees, depends on the engine design anyway. So, the injection takes place, injection of fuel takes place about 20 degrees crank angle rotation, started just before the top dead center, it's about 15 degrees before the top dead center, and can go to about 5 degrees after top dead center. And injection pressure is usually very high. Of course, in addition to the push, tumble and swirl that we generate, and as a result of that the turbulence, we need very high injection pressure or the injection velocity to spray fuel into high pressure air for the proper mixing and combustion to take place. Now in diesels, the combustion takes place in about 4 different stages. As in the case of petrol, there is certain ignition delay. Then there is a pre-mix combustion phase, and then mixing controlled combustion phase, and then finally the late combustion phase. If I show you a small video clip about this the injection, diesel injection, as you can see, the injection takes place all around the combustion chamber, radially outwards, as you can see here. As you inject, the combustion takes place. It's not pre-mixed combustion, it's more or less diffusion combustion. Now, so these are some more pictures how this flame propagation takes place. So, as in the case of petrol combustion or the gasoline combustion, there is an ignition delay in compression ignition as well, the diesel combustion as well, where initially as you spray the fuel, now for combustion, of course, fuel and air has to be mixed up, otherwise the combustion can't take place. So, fuel and oxygen is needed for combustion. So, it takes a little bit of time to mix the droplets of fuel that are sprayed into the high pressure air. It takes a little bit of time for this mixing initially, for the initiation of combustion. So that is the ignition delay period. And then as the droplets of fuel mix with air, then there is kind of pre-mixed combustion phase taking place as in the case of petrol. So next, after pre-mixed combustion, then the mixing control combustion takes place. That is, the burning rate would decide how the mixing of fuel and air would take place, and as they mix, they burn. As they mix, they burn together with air. The combustion during that phase is mixing controlled combustion. As you can see, this is the start of injection and this is the end of injection, and after that there can be some late combustion phase where the end parts, leftover particles, the fuel particles would burn lately. So those are the stages in combustion, in compression ignition delayed. That is the time taken for the atomized fuel particles to mix with air particles, penetrate into combustion chamber and mix with air particles. And then comes pre-mix combustion phase, where the already mixed during air and fuel in the ignition delay period would start burning. And then comes the mixing controlled combustion, where the burning rate, as I said earlier, decides how the mixing would take place for combustion. And then late burning, of course, that is the last part of the combustion, and that is how the diesel is burnt in internal combustion engines. So this is the pressure diagram, where this is the point of injection, B is the point of ignition, and this is the end of injection. So the pressure rise is something somewhat different to the pressure rise in the spark ignition engines. And as I said earlier, there are two different types of compression ignition. One is called the direct injection, and there are two different parts of fuel injection in compression ignition: direct injection and indirect injection. I discussed about those things. I'm not going to go into details. There are two types of direct injection. In fact, radial injection, as you saw in the video that I showed you. So this kind of combustion chamber is called the crescent type combustion chamber. At the center you have this injector, and the injection takes place all around. And then there is another type called swirl type, with deep ball in the piston, where the swirl generated turbulence would ensure proper mixing for combustion. And of course, indirect injection, there is a pre-chamber where the injection and combustion takes place initially at this pre-chamber, and the burn gases will come out to the main combustion chamber afterwards. And generally, for very large engines, if the engine size is very large and operate at low speeds, then you have more time for mixing. The time for mixing is more in the case of low speed and large size engines. Therefore, we usually use direct injection crescent chamber shape, open shallow bowling piston type. That is this type. This type is used for large size slow speed engines, because you have plenty of time available for this mixing of gases, the mixing of fuel with air. And then as the engine size decreases, the engine speed is increased. Then again you need to have certain degree of turbulence for mixing and quickly burn the gases. So when the speed is increased, the time available for burning reduces. So the combustion should take place quickly. So the swirl is used for mixing, Therefore, these deep ball in piston type swirl chambers are used for situations where the load is size of the engine is smaller but operate at very high speeds. And then small size engines, small size high speed engines, mostly the engines that we use in automobiles. Of course, if the engine speed is too high, then the turbulence generated from swell, push, and tumbling flows may not be adequate. In such situations, indirect injection engines are used. So, for example, now if you consider these tractor engines, tractors are operated at low speeds, and engines are heavy, big. So, the direct injection technique is used in those, whereas indirect injection is used in mostly small size, high speed engines like automobile engines. And of course, I will skip these slides because I explained these things in one of my previous lectures about injection techniques, the conventional pump technique as well as command rail technique. Basically, there are two different types of diesel fuels used in compression ignition engines: light diesel fuel and heavy diesel fuel. The light diesel fuel is the one that we use in most automobile engines, where you have a less viscosity, and as a result of that, the pumping of diesel is easier with light diesel, and you can make them into small droplets through injector, so that can be easily used for automobile type applications. But again, the downside of it is, of course, the light diesel is more expensive than heavy diesel. The molecular weight is about 170, whereas heavy diesel, the molecular weight is about 200. The chemical formula for light diesel is this one, and of course, this is the heavy diesel. And heavy diesel is usually used for industrial applications like power plants or huge engines. And of course, just because they are cheap, this heavy diesel is used. And now we discuss about octane number when we talk about the petrol combustion or the gasoline combustion. Whereas in diesel combustion, there is something called diesel fuel, for example. There is something called cetane number, which describe mostly the ignition delay of a particular fuel. Now, the octane number describes the tendency for knocking, whereas cetane number describes how long the fuel will take before it gets auto-ignited. So, the larger the cetane number, shorter the ignition delay is, so that you could burn quickly. Like in the case of octane number, the cetane number also calculated with reference to certain standard fuels. So, N-cetane is considered as cetane 100, and heptamethanol is considered as cetane 15, and any fuel we could have a number, cetane number between 150. And this chart gives you some numbers about these various different properties of fuels. Now, if you look at cetane number of light diesel, it's about 40 to 55, and heavy diesel it's about 35 to 50. So the cetane number is around that range, whereas the octane numbers are usually close to 100, that is in the range of 90 to 100. So, and various other heating values and stoichiometric air flow ratios and things like that are given here just for your information.